All right, everyone. So today we're gonna cover laws of exponents, right? And so those are laws that basically deal with the manipulation of things to different powers. So like three to the second power, three to the third power, things like that, right? And so what I want to discuss is like the three most important laws of exponents, which basically means the three tools that you use the most when you're manipulating an expression that involves exponential powers, right? So let's dive into the first law. It's called law number one, which basically states that two numbers, let's call them A, well, it's the same number, but we're going to deal with it twice in this law. A number with the same base to different powers, right? So we have a to the k, for example, times a to the m. So we're multiplying two numbers with different powers, but the same base, right? And so this law basically states that a to the k, where a and k are some numbers, times a to the m, right, where a is the same number in both cases, can be simplified, right, to a to the k plus m, right? So we can essentially add the powers there, right? So let's get into why this is true, right? Why can we do this for any case? Of course, we can prove it, right? So let's do a quick proof of this. So let's assume we have, let's take 3 to the second, for example, just like I discussed in the beginning here. 3 to the second times 3 to the fourth, right? So we have our, in this case, right, the 3 would be kind of like our A, right? The base in each case here is 3. And our k would be 2 and our m would be 4, right? But it really doesn't matter what we call them. All that matters here is that we're multiplying two exponential expressions with the same base, right? And so by our law here, we know that this is 3 to the 2 plus 4, right? Which gives us 3 to the 6th, right? Great. But why is this true, right? So the way to kind of prove this law here is we have to look at, okay, what is 3 to the second actually saying? Well, we know it's saying 3 times 3, right? Because we have 3 squared, which is 3 multiplied by itself twice, right? And then we're multiplying this by 3 to the fourth, right? And 3 to the fourth is just 4 threes being multiplied by one another, right? 3 times 3 times 3 times 3. And so now we can see why this law is true, right? Because simplifying this expression down, right, if we were to remove the parentheses, which I'll do now, then we see that all we have here, and we can see it explicitly now, is 6 threes, all being multiplied by one another, right? And so, well, what's 6 threes being multiplied by one another? Well, that's just 3 to the 6th, right? And so we can imagine if we took 5 to the base, 6 to the base, any number to the base, right, when we expand them like this, we're always going to see that those exponents are going to add, right? We're going to see when we expand them out that we're essentially, instead of just adding the exponents, we're actually multiplying the number out by the times that the exponent is added, right? So because we had a 2 and a 4, we multiplied it out by 6 times, right? Because it's 3 squared times 3 to the fourth. Right, so that's kind of the first law here. Okay, great. So I'm going to erase this, and now we'll discuss the second law, and at the end I'll list all of them, right, just for clarity here. So the second law here is very similar to the first, right? We're dealing with, I'll use a again, right, a number, right, to the power of k, right, where a and k are both numbers, and then we're raising this whole expression to m, where m is another number, right? And this law states that this, for any numbers a, k, and m, right, we will get a to the mk, m times k, where basically we're multiplying out those powers here. And so, well, similarly to the first, we can take a look at the proof, right? So why is this true, right? Well, let's take a random case. Let's take 5 to the fourth to the fifth, right? In this case, our k is 4, our m is 5, right? Could be anything, and our base a is also 5, right? Any numbers, right? And so the law says, okay, this should be 5 to the 20th, right? Just based on, we're multiplying out those powers here. 4 times 5 gives us 20, right? Okay, so why is this true, right? Let's take a look at why it might be true. Well, let's look at, say we had some number x to the fifth, right? We know x to the fifth is just x times x times x times x times x, right? And so in this case, we're just looking at 5 to the fourth to the fifth, right? Which is just 5 to the fourth times 5 to the fourth out 5 times 5 to the fourth, right? And we're doing that 5 times, right? Great. That's what this 5 here with the bracket means. So, well, we can further expand this expression, right? Let me just erase this because I'm running out of room. We can further expand this expression, right, as 5 times 5 times 5 times 5. That's 5 to the 4th, right? Times 5 times 5 times 5 times 5. That's also 5 to the 4th, right? And we're doing that 5 times, right? So now, like in Law 1, we've essentially broken everything down into just 5s. And we know that if we multiply 5 out 4 times, it's 5 to the 4th. If we multiply 5 out 5 times, it's 5 to the 5th. And so if we were to count all these 5s here, we'd see 25s, right? Because we're multiplying 5 to the 4th out 5 times, right? So we have 4 5s multiplied out by themselves 5 times. So in the end, we would end up counting 25s. So this would be 20, which gives us an answer of 5 to the 20. And you can imagine this law would hold true of any numbers because the operations would stay the same, right? I've just done an example with 4 and 5, but this law is true for any number, right? Great. Just going to erase this. I'll, again, put them all back at the end. Let's take a look at the final law of this video, which is going to be kind of a bit of a stranger law, but it's very useful, right? It's just kind of the opposite of that first law we discussed. So we'll take a to the k divided by a to the m. This is law 3, by the way, is equal to a to the k minus m, where obviously k, m, and a are any number, right? So let's look at the proof of this again, right? Kind of a similar pattern, right? So let's say I had 5 to the 4th, right? A is the same base, divided by 5 to the 3rd, right? Well, the law tells us this is 5 to the power of 4 minus 3, which is just 5 to the 1st. Which is just 5, right? Because any number to the first power is itself. And so let's take a look at, let's expand this out and see why it's true, right? So based on the first examples, we know 5 to the 4th is 5 times 5 times 5 times 5. 5 multiplied out by itself 4 times, right? And then we divide by 5 multiplied out by itself 3 times, right? And we know that, you know, based on division, right, the laws of division, we can cancel out. If we have an expression, we can factor it out into its parts, just like we've done here, and we can cancel out the common parts, right, just by the properties of division, right? So we can cancel out this one, right, because it's the same on the top and bottom. We cancel out this one, it's the same on the top and bottom. We can cancel out this one, it's the same on the top and bottom. And all we're left with at the end of that is 5 to the 1st. So essentially what this law is saying is that we can cancel out common factors. We can subtract exponents when they're the same, right? So it's kind of the opposite of that multiplication law where we can add exponents depending on the number of times we're multiplying out something. Here we can subtract exponents, right? We're essentially dividing out those extra powers, right? Great, and this would hold for any numbers. You could repeat the same process. One thing I should note here is that you'll have cases like this, right? So I'm going to do a separate example here. Where, you know, the numerator and the denominator, they're not necessarily produce a nice positive exponential result. And I want to kind of do this example here. We could have 5 to the 2nd divided by 5 to the 3rd, right? And using that third law here, this would be 5 to the 2 minus 3, which is 5 to the negative 1. And you might be, whoa, that's kind of crazy, right? 5 to a negative power, right? So that's kind of what I want to talk about now. Like, what is 5 to the negative power? Well, we know this law is true, right? So to figure out what 5 to the negative power is, we might do the exact same thing I did to prove this law, where you could take a look at this and say, oh, well, this is just 5 times 5, right? Divided by 5 times 5 times 5. Well, we know these two are going to cancel because they're the same. These two are going to cancel, so they're the same, right? And so that's equal to 1/5. And so now it's like, oh, okay. Now we know what 5 to the negative 1st is, right? We've just essentially expanded it out, and we've shown that this is equal to 5 to the negative 1. And so 5 to the negative 1 is 1/5. And so in general, right? What about any number to the negative 1? This is kind of one of the topics I wanted to touch on because it shows up a lot, right? What about if we had like a number like n to the negative 1? What might that be, right? So what is n to the negative 1? How can we show that any number to the negative 1, what is it, right? How can we show it something, right? We just showed that 5 to the negative 1 is 1/5, right? So what's n to the negative 1? Well, I'll tell you right now, you may have guessed this already based on the 5 example, that n to the negative 1 is just 1 over n, right? It's quite nice. We have this kind of fractional negative exponential property going on here based on that third law here, right? And so how do we prove this for any number, right? Well, the way we prove it, right, is we just take a look at 1 over n, right? And we'd use the fact that n to the 0 is equal to 1 for any number n. And why is this true, right? So first we kind of have to introduce the fact that n to the 0 is 1. And so I'll do it over here, right? But the key thing to notice is that if I had a to the 0, right, that's the same as a to the, we'll call it L minus L, where L are the same things, right? And so we can kind of apply this law in reverse, okay? So a to the L minus L, based on this third law here, implies that we have a to the L over a to the L, right? That's a to the L minus L, right? Just based on the law of exponentials, right? The third law, right? We're just reversing that process here, right? And well, we know from division, right, that any number divided by itself, a to the L is the same as the top and bottom, right, in this case, right? Any number divided by itself is just 1, right? And so we know that this is just 1, right? And we know that this is a to the 0, right? Because we're subtracting those exponential powers, right? And so now, based on this, we've just shown mathematically that any number to the 0th power, assuming it's not 0, we're going to exclude that case because you can't divide by 0, right, is 1, right? Okay, let's bring it back here, right? We know that now n to the 0, same as a to the 0, is equal to 1, right? Okay, so the step here, the next step here now is we have to show that n to the negative 1 is 1 over n. Okay, great. So I'm going to erase this, right? Erase this. So we're going to prove that. Okay, how do we prove it? Okay, well, the first step, right, is we need a reminder to remind ourselves, right, that n to the 0 is 1. And so if we want to find what let's apply this process in reverse, right? We know that, therefore, 1 over n, right, is equal to n to the 0 over n, right? Because n to the 0 is just 1. So this is pretty nice, right? Because we know that n here in our denominator is just n to the 1, because by definition, any number to the first power is just itself, right? We can prove that similarly, but I'm not going to. It's a pretty standard fact, right? So based on this, right, we can now show that n to the 0 minus 1 is equal to 1 over n, right? And well, what is that, right? N to the 0 minus 1 is just n to the negative 1, right? Great. So we've just shown that. N to the minus 1 is 1 over n. Great. Okay, so now I'm just going to write up the 3 laws here, right? Because these are important to memorize, and I'll do another video with some practice problems with just these 3 laws. There are, of course, more. We'll do a different color here just to make it nice and clear, right? So we have our 3 laws. And I'll give them names now just to help you guys remember it, right? So 3 laws. Great. So we have the law of, we'll call it the law of, I think it's probably better we leave out the names for now. Just don't want to get confused, right? So law 1, of course, is a to the k times a to the m, right? We proved this one where there are any numbers, right? A, m, and k are any numbers. All that matters is a is the same base in both cases, is a to the m plus k. You put in parentheses if you like, you don't have to, right? That's the first law. I'll do the second law in a different color. So law 2, it's the second law, right? We have a to the k all to the power of m, right? So it's a little different. This is different than the first one in that we're taking the whole expression to the power of m. We're not multiplying 2 things, right? We're essentially multiplying out a to the k m times, right? And so this is going to give us, as we proved, a to the km or a to the mk. It's multiplication. You can do it either direction, right? Great. So now finally we have that third law. Do it in blue here. Kind of the most interesting one in my opinion, but you can choose your favorite here. Is a to the k divided by a to the m is equal to a to the k minus m, right? Great. So we know these 3, great, perfect. These are those 3 laws, right? And then the last thing I'm going to do, right, just to sum up this video, I'm going to erase this, right? You can write it down, keep a note of it, great, right? I'm going to just write up that last law, right, that kind of most important one. or one of the most important facts, takeaways from this video, right, is that negative exponential, right? It looks kind of scary at first, but it's not, right? We have a definition for it. Great. So it's n to the negative 1, right, is equal to 1 over n, which kind of relates negative exponents to fractions, where the numerator is 1, the denominator is n. This is saying that 3 to the negative 1 is 1/3, right? 4 to the negative 1 is 1/4. And n to the negative 1 is 1 over n, right? Any number can even be a fraction, right? You just got to remember how to manipulate it properly. All right. And then the last takeaway, right? We know that n to the 0 is equal to 1, which means 3 to the 0 equals 1, 2 to the 0 equals 1. Great. So any number to the 0 is 1, right? Okay, so, to wrap it up, let's take a look at one example. And then in the next video, I'll cover more practice problems. I'm just going to erase the whole board here. We'll do a more complicated example. These problems often look complicated. They can look intimidating, but they're not. And the reason is, all you're doing is simplifying. You're not actually solving for anything, right? So all you have to do is remember the laws and remember order of operations, basically, right? We have to combine everything properly. We don't want to miss any negative signs, right? We want to make sure we're considering everything in the problem. Look at it carefully, right? So I'm going to put out one problem. We'll call it problem 1. I'm going to say simplify, right? And I'm just making these off the top of my head here, so it may look a little crazy, but I promise it's not. I'm going to take a new number z, right? Z is just a number. Right now, it's a variable that represents any number, right? We're going to have z to the negative k, right? Perfect. Oh, sorry. We're going to have z to the negative 1 times z to the 4th over k cubed, right, that the second law is coming here, squared, times some random variable r, right? So it looks kind of crazy, right? But if we look carefully, it really isn't, right? Because all we have at the top and bottom, and we know you can see it, right? Because we have two same bases, right? And we have different powers. So that's law 1 right there being applied, right? And then in the bottom here, we have law 2 being applied. We just have that whole expression all to the power of a different number, right? That's law 2. And then over here, use green for that. All we have is just some random coefficient variable here that's just being multiplied by the whole thing, right? So all we have to do is multiply that out, right? Great. So let's simplify it. Okay. So you guys can see this, great. Just making sure. Let's apply that first law here. So based on the first law, we're just adding the powers, right? So we have negative 1. I don't want to make that error here. Negative 1 plus 4, z to the negative 1 plus 4, right? Based on the first law. Divided by r. Nothing happens to r, just get multiplied by this, right? R times k to the power of 2 times 3, right? That's that second law in place. Right, great. And that's going to, we can just finish up the problem here, not that much left to do. We just have to combine this, which is going to give us 3, because 4 minus 1 is 3. It's still positive here. And this is going to give us 6. And so we have a final answer of z cubed, or z to the 3rd power, over r times k to the 6th. And that's perfectly acceptable, right? So you started off with this whole crazy thing right here, and you're left with this nice-ish answer, right? So that's really all there is to it. You just have to remember the laws. Once you know the laws, I will introduce more laws in the future. All it comes down to is just applying them, right? That's all it is. It's really nothing crazy. The more problems you do, the more comfortable you'll get with it, right? Great, so I hope this was helpful, and I will see you in the next video.